This paper presents a microscopic statistical theory of phase equilibria in non-crystalline block copolymers. The authors aim to explain how and under which conditions the incompatibility of molten copolymer constituents leads to the formation of different ordered structures, mesophases. The specific focus of this paper is on the onset of an ordered mesophase from a homogeneous melt and the criterion for microphase separation. The authors begin by discussing the unique properties and morphologies of block copolymers, which arise due to the incompatibility effects between different sequences of monomers. These effects result in microphase separation, where microdomains rich in one sequence are formed. The authors note that while the existence of mesophases in block copolymers has been established experimentally, there is still limited understanding of the conditions of microphase separation. To address this knowledge gap, the authors propose a microscopic theory based on statistical physics. They use a generalized random phase approximation method to study the monomer density correlation functions in the disordered phase of block copolymers. They find that under specific critical conditions, an unstable mode with a non-vanishing wave vector appears, indicating the onset of microphase separation. The authors then derive the free energy of the block copolymer system in terms of the order parameter of the microphase separation transition. They identify two relevant parameters for characterizing phase equilibria: the composition F, fraction of monomers A in a chain, and the product Xn, where X is the Flory parameter characterizing A-B interactions and N is the polymerization index. Using these parameters, the authors calculate the regions of stability for different phases in a phase diagram of the system. The authors also discuss the symmetry and periodicity of the mesophases that appear after microphase separation, as well as transitions between mesophases with different symmetries. They propose a new method for measuring the interaction parameter X using small-angle X-ray scattering. Overall, this paper provides a theoretical framework for understanding the microphase separation transition in block copolymers and offers predictions for the phase behavior of these systems. The authors emphasize the importance of further experimental verification and the need to determine the interaction parameter X accurately. The figure shows the scattering intensity, S, Q, as a function of the interaction parameter X for different values of Xn. Xn is the product of X and N. The figure illustrates that as Xn increases, the peak in the scattering intensity becomes more narrow and its maximum value increases. The peak corresponds to the microphase separation transition in the molten copolymer. The position of the peak, Q, does not depend on the monomer interactions, but its shape and height depend on the value of Xn. The figure shows the plot of the product Q2R2, where R is the radius of gyration of the copolymer chains, versus the composition F of the copolymer. The plot illustrates that for small f, Q increases rapidly, indicating a larger periodicity in the microdomain structure. The figure shows the scattering intensity S, Q, as a function of the interaction parameter X for different values of Xn. The plot illustrates that for larger values of Xn, the peak in the scattering intensity becomes more narrow. The position of the peak, Q, does not depend on the monomer interactions. The figure shows the spinodal point, xnt, as a function of the composition F of the copolymer. The spinodal point determines the limit of metastability of the system. When the system is quenched to the metastability region, microphase separation can occur. The plot illustrates that the spinodal point depends on the composition F. The figure shows the coefficient nr3 as a function of the composition F of the copolymer. The coefficient R3 is related to the third-order term in the free energy expansion. The plot illustrates that R3 is negative for all values of F, indicating that the microphase separation transition is a first-order phase transition. The figure shows the coefficients nr4, 0, 0, nr4, 0, 1, and nr4, L, 2, as a function of the composition F of the copolymer. The coefficients R4 are related to the fourth-order term in the free energy expansion. The plot illustrates that nr4, 0, 2, is larger than nr4, 0, 1, for all values of F. The figure shows the coefficients nr4, 0, 4/3, and nr4, 4/3, 4/3, as a function of the composition F of the copolymer. The coefficients R4 are related to the fourth-order term in the free energy expansion. The plot illustrates that nr4, 0, 4/3, is larger than nr4, 0, 0, for all values of f. The figure shows the phase diagram of the copolymer as a function of the composition f. The phase diagram shows the transition lines from the disordered phase to the BCC phase, from the BCC phase to the hexagonal mesophase, and from the hexagonal to the lamellar mesophase. The plot also shows the spinodal point, which determines the limit of metastability of the system. The plot indicates that the lamellar phase is the most stable phase for all compositions. The discussion and conclusion of this scientific paper focuses on the phase diagram of amorphous D-block copolymer melts. The authors conclude that the state of the system is determined by two relevant parameters: the copolymer chain composition and the product of the Flory interaction parameter and the number of monomers in the chain. They present a universal phase diagram that shows the regions of stability of different phases based on these parameters. The authors discuss the disordered phase, which is characterized by a homogeneous distribution of monomers, and the strong segregation effects observed in copolymer melts. They compare the behavior of copolymers to that of mixtures of two homopolymers and highlight the difference in critical points for demixing. The authors predict that the microphase separation transition in copolymer melts is a first-order phase transition from the disordered phase to a mesophase with the symmetry of a body-centered cubic lattice. They also discuss the possibility of other stable phases, such as triangular and lamellar microdomain structures, near the spinodal of the copolymer melt. The authors mention experimental observations that support their predictions, including the existence of different mesophases in phosphorus monosulfide Pb copolymers and the stability of the lamellar phase in phosphorus monosulfide Pi copolymers. They also acknowledge the limitations of their theory, including the neglect of fluctuations with wave vectors different from the ordering vector and the need to include the effects of polydispersity. The authors express their hope that further experimental studies will verify and refine their phase diagram. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.